Welcome to Lecture 13. In this lecture, we will introduce what is meant by greedy algorithms. We will give several examples. They include the activities selection problem, the fractional knapsack problem, the vertex cover on rooted trees. This problem, we have studied it already in the dynamic programming part, but here we will revisit again. And finally, we will talk about something called the Huffman Code. So let's start. Okay, now let us consider the following coin changing problem that will appear in our daily life. So suppose that in a certain country, there are different coins, and then each value of a coin can be one of the following. So we could have something like a $1 coin, a $2 coin, a $5 coin, and a $10 coin. We want to get a certain amount Z using the fewest number of coins. So naturally, what we will do in our daily lives is like that. We will see how many $10 we should give out. We will use $10 as many as possible. And after that, we will try to use $5 as many as possible. And then $2 as many as possible. And finally, we will get the correct amount using the $1. So let's see this example. So for instance, to get $39, so we would have used what? So starting from 39, we try to give out $10. So we will find out that we can give out 3 of the $10 so that we will get $30 at this point. Now the remaining part will be $9, so we will give out $5. And then after that, we will give out $2 and $2. So altogether, there are going to be 1, 2, 3, 4, 5, 6 coins. So we are using 6 coins. In this method, we will repeatedly give out coins with the largest possible value, and until the total sum of the coins that we have given out is equal to the amount that we want to get. So in some sense, we are trying to do what? We are trying to drop the remaining amount as fast as possible. So it is more likely that we will be using fewer number of coins in the future. And this is an example of a greedy algorithm. So here, once again, let us recall, we want to get the fewest number of coins. So naturally, but this is not always true, but naturally what we were doing was we try to give out the largest amount. By doing so, we will try to drop the problem into a smaller subproblem, and then we want to drop it into as small as possible the subproblem that we could have. And here, so in that case, so this is why this is greedy. It is because we want to get few, so we will give out large value. So this is kind of something that we call it greedy. So the two key properties for a greedy algorithm is like this. So each time we will make a choice, and this choice seems to be good towards getting the best answer. So we call this the greedy choice. And then after a choice is made, we will transform the original problem into a subproblem. So we will make the original problem into some problem that looks like the same type of problem as before. So because of this, because it is of the same type of problem, then we can reapply the same technique again. So we will have the greedy choice at the time, and then get into a smaller subproblem, and so on and so forth, and then we will solve the problem finally. Now usually for a greedy algorithm, the optimal substructure part is usually easy to see, as long as we will see that the problem looks the same type as before. But so the design of a greedy algorithm, the most difficult part is actually showing why the greedy choice is working. So in particular, we need to show that the greedy choice that we make is not wrong. Now in the previous example, the method seems to be correct. So trying to get the largest possible value each time repeatedly until we get the total amount. But consider the following example. Suppose that in a different country, the coin values are not like 1, 2, 5, 10, but it has only 1, 4, and 5. So we have just 3 types of coins. And the total amount Z that we want to get is 8. Now in such a case, using the previous idea, we will try to give out $5, and after that the remaining amount will be 3. So we will give out 3 coins of $1. So altogether we are sending 5, and then 1, and then 1, and then 1. So altogether there are 4 coins. On the other hand, with the special coin design in this country, to get a total of 8, we could have given out 2 coins of $4. So in that case, trying to send out a coin with the largest possible value each time may not work. In particular, for this country, it is wrong. So that's why the greedy choice that we make is not necessarily working, and then we will need to be very careful in order to show a greedy algorithm is correct. So this is usually the most important part, to show the greedy choice that we make is not wrong. So let us see our first example. It is called the activities selection problem. So here there are n activities that we want to join. Each activity has a different starting time and finishing time. So here we will use the horizontal bar to denote each bar here that we are showing denotes a particular activity, and the length of this interval or this box corresponds to the left side boundary is the starting time, and the right side boundary is the finishing time. So if we want to join this activity, then we will start at somewhere like 9 a.m. and then it ends at something like 12 in the noon. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 activities that we want to join, but we cannot join activities whose duration overlap. So suppose that we are joining this activity. Then in that case, since this activity overlap with this one in the duration, so if we pick this one, then we cannot pick this one. If we pick this one, then we cannot pick this pale blue one. And the target here is we want to join the maximum number of activities. So how to decide which activities to join? Okay, now to join as many activities as possible, it seems reasonable to have the following different ways of picking the activities. So the following ways are all like greedy choice. So for instance, we may try to pick activities such that it has the shortest duration time first. So if you pick an activity with the shortest duration time, that means that it only occupies a very short period of time. So we will still have a lot of time remaining so that we can pick more activities. So in that case, this kind of idea seems like we are trying to get the maximum activity using this kind of, like this idea. Now the other one is earliest start time. So we will look at activities such that the starting time is the earliest possible. Because if we pick an activity that starts early, then once it is finished, we can immediately pick another activity such that in the remaining parts that we can pick, we pick one which can start as early as possible so that we can get more and more and more. So this seems to be another reasonable choice in order to maximize the number of activities that we are joining. Now the third idea is we get the earliest finish time. So the third idea seems to be similar to the shortest duration time, because by picking one that has the earliest finishing time, so we will try to get the first activity so that it ends early, so that immediately we will have more time remaining so that we can pick another activity again. So all these choices here seems to be reasonable. And then let us analyze whether they will really lead to a correct algorithm. Okay, so let us take a look of the so-called shortest duration time. Now here, for the shortest duration time, we will see one example below that it shows that it is not optimal. So in this diagram, we will see that there are altogether only 3 activities. The blue one has the shortest duration, while the other 2 doesn't. And then, if you look at the best way to pick activities, we can pick the bottom 2 activities because they do not overlap, so that we can carry out these 2 activities together. On the other hand, if we pick the shortest duration time activity, we'll pick this blue one. Then in that case, once we have picked this one, we can never pick the bottom 2 anymore, because it overlaps with the other 2 activities. So by taking the shortest duration time activity, we will only get 1, but the optimal is actually 2 here. So we will see that this idea will not give us optimal solution. So if you want optimal solution, this is a wrong idea. But on the other hand, although this is not an optimal way of choosing activities, we can show that the number of activities selected by using the shortest duration time first, so we will repeatedly pick the shortest duration time activity again and again and again, then it's not that bad. It is always greater than or equal to the number of activities in any solution divided by 2. So here, in any solution, it means that not just, in any solution, so including optimal solution. So the number of activities using this greedy choice, shortest duration time first, may not be optimal, but it is at least half of the optimal. So if optimal can allow you to select 10 activities, so if you cover my eyes, I will immediately tell you that the shortest duration time first, this greedy choice will give at least 5 activities. So it's not that really bad. Now, how about the second way, the second type of greedy choice? So here, suppose that we pick activities repeatedly according to the earliest start time. Now, in such a case, the solution can even be worse. So look at this following example. So we have many activities in the top row. So all these activities, we can carry out them together without any problem because their time, the duration time, does not overlap. But on the other hand, if we select the activity with the earliest start time, so we will be picking this blue one. Once we have picked the blue one, we can never pick any more activities in this example. So in that case, what we have selected is only 1 activity, while the solution can be like n-1 activity. So here there's no bound between the number of activities selected by earliest start time with the number of activities in the optimal solution. So this is even worse. So in the previous one, so let's get back to the previous one, it's not optimal, but it is at least half of the optimal. Okay, and here, for this one, there is no bound. So the optimal could be way, like order n times better than the earliest start time method. Now finally, and surprisingly, if we select activities using our third type of greedy choice, earliest finish time first, then this will be optimal. So this was our first example. So in our example, we will be selecting this orange one because it has the earliest finishing time. After that, we take out the activities that overlaps with it because they no longer be selected. And among the remaining, we will pick one that has the earliest finishing time, so we will pick this one. After this, we will cancel this one because they no longer can be selected. And among the remaining, we will pick this one. And finally, we will pick this one. So this is the earliest finish time first choice. And why is it optimal? So this is the hardest part of the greedy algorithm. So we need to show why this works. So let's see. So the following is our reasoning why this is a good choice. First of all, let us use A to denote an activity with the earliest finishing time. Our target here is we want to show that some optimal solution will also select A. Now, there could be numerous optimal solutions. There could be more than one optimal solutions, as long as they give the maximum number of activities. So we want to show that among all these optimal solutions, some of them will also select the same activity A here as we do. So if this is happening, this means what? This means that at the moment, our greedy choice is not wrong. Now notice that we do not need to require every optimal solution must select A. As long as some of them selects A, that's already good. Now how do we show this? Okay, so we don't know. So let's imagine that there is a certain optimal solution. Let's use OPT to represent it. So this optimal solution corresponds to a set of activities, and these activities has the maximum number and they are not overlapping in the duration time. Now first of all, if this set of activities contains A, then we are done, because we are not that ambitious. We just want to show that some optimal solution will select A. So if this opt already select A, then done. This is our purpose. Now on the other hand, suppose that opt does not select A. Then in that case, opt must have an activity, let's call it A prime, that overlaps with A. Now if this is true, it is because if there is no activity A prime, or there is no activity overlapping with A, then we can include A in the optimal solution, because the duration does not overlap, so we can have A as well. But then this will give us a contradiction, because optimal already has the maximum number of activities, so we cannot add any more to it without any problem, right? Because of this, opt must have some activity, let's call it A prime, that overlaps with A. And moreover, this A prime is the only activity that can overlap with A. It is because if there are two activities, so let's take a look of this one. So this is the A that we have in this example. If there are two activities overlapping with this one, then one must look something like this and the other must look something like this, right? So the one that is earlier must have a finishing time before the finishing time of A. And that will give us a contradiction, because what? A is the activity with the earliest finishing time. So in that case, we have established that opt, if it does not contain A, must have exactly one activity, A prime, that overlaps with A. Okay, then in such a case, what we can do here is that let us take away A prime from opt and then put A into the remaining part of opt. So we are taking away A prime from opt but replacing it by A. Then we will see that all the activities do not overlap, because A is overlapping with only A prime in opt. So taking away A prime, putting A inside, A will not overlap with any other activities with opt. But certainly, the resulting set, so we have changed opt into some other thing, right? But the resulting set of activities will have the same size as the original opt, because we have taken away one activity, but we put it back, put one activity back. So the number of activities is the same. So we will have the same activities, not overlapping with each other, and then with the same number of activities as opt. So what does that mean? So this is another optimal solution. And suddenly, this optimal solution that we have just derived will now contain A. And this gives our purpose, because previously we want what? We want to show that some optimal solution will select A. So here, even though we start with opt that does not select A, but in the end, we have proven that some certain optimal solution contains A. Now the previous proof, if we revisit again, the idea here is it begins with some optimal solution opt, and we replace some choice inside this opt with our greedy choice. So opt may not make the same choice as we do, but we will try to replace some of its choice with our greedy choice and show that it works. It is another optimal solution. Now, this is something that we called a cut and paste argument. So it is like the Control X, Control V thing in our word, right? Now, because the greedy choice is not wrong in such a case, then it implies that we can make such a choice and then focus on finding optimal solution that must include the greedy choice. So greedy algorithm has this idea. Greedy choice is not wrong, so we make it and worry about things in the future, not at this moment. As long as we are not wrong, we make this choice. And after that, we will focus on anything that makes this compatible. So we will find optimal solution in the future that must include the greedy choice. And this becomes a subproblem, and so recursion applies. Okay, so this is the description of the activities selection problem.